For decades, we've had this official guidebook to the cosmos, a masterpiece of science that explains pretty much everything. But today, we're going to look at the fascinating and kind of scary cracks that are starting to show up in its pages.
So, let's just imagine for a second. You've got this beautiful, detailed map of the world. You trust it. But then you start hearing reports that maybe it's missing entire continents. That's exactly the feeling that's spreading through cosmology right now. We have this incredible map of our universe, but it's starting to look like it might be incomplete.
Okay, so before we dive into the weird stuff, we gotta get our bearings. We need to understand where we are right now. And our current address in the cosmos is described by this magnificent theory, the Standard Model.
Now, it has a kind of clunky name, Lambda-CDM. For decades, this model has been stunningly successful. It explains almost everything we see, from the leftover glow of the Big Bang all the way to how galaxies form these giant cosmic webs. That first part, lambda, that's just the Greek letter scientists use for dark energy, and we'll get to that in a sec. This thing really is our official guidebook.
But here's where that guidebook reveals a truly bizarre recipe. Look at this. The Standard Model tells us that everything we can see and touch, stars, planets, you, me, all of it, makes up just this tiny little 5% sliver of what actually exists. The other 95%? Well, it's dark. These two things are the invisible pillars holding up the whole model. Think of dark matter as this invisible cosmic scaffolding. It provides the extra gravity that keeps galaxies from just flying apart. And then you've got dark energy, that's our lambda, which acts like a kind of cosmic anti-gravity, pushing everything apart, faster and faster.
But, and there's always a but in science, right? This elegant, incredibly successful picture, it starts to get complicated. Because when we point our best telescopes out there and make super precise measurements, the numbers just don't add up.
And this slide right here gets to the absolute heart of the problem. We have two completely different, totally reliable ways to measure how fast the universe is expanding. The first method looks way back in time, at the afterglow of the Big Bang, and it gets one number. The second method looks at things closer to us, like exploding stars, and it gets a different, faster number. And this isn't just a small rounding error, folks. This is a fundamental disagreement. Scientists call it the Hubble tension, and it's a huge.
This discrepancy has become one of the biggest puzzles in all of physics. It has everyone asking this profound question. Did we mess up one of our measurements? Or is our standard model, our trusted ruler for the entire universe, somehow broken? Is there a key piece missing from the puzzle?
And it's not just the expansion rate that's causing headaches. That other mystery, dark matter, the stuff that supposedly makes up a quarter of our universe, well, it's completely ghosting us. For decades, we've built these incredibly sensitive detectors deep underground, trying to catch just one particle of it. And we've found absolutely nothing. Zilch. Which leads to a pretty wild question. Are we even looking for the right thing? So when your standard story starts to fray at the edges like this, what do? Well, you start thinking outside the box. Way outside the box. Physicists are now being forced to question our most basic assumptions about reality, starting with time itself. Enter a theory with a really cool name, Timescape Cosmology. And as this quote says, it makes a heck of a bold claim. It suggests that maybe we can have a working model of the universe without needing dark energy at all. How? By completely changing the rules of time. Okay, stick with me, because this is wild. The Standard Model just assumes there's one universal clock, ticking away at the same rate everywhere. But Timescape says, hold on, what if that's wrong? It proposes that time actually flows at different speeds depending on where you are. A clock inside a crowded galaxy like the Milky Way might actually tick slower than a clock out in the vast, empty voids between galaxies. Now just think about what that means. If time is flowing faster out there in the empty spaces, then distant galaxies would look like they're rushing away from us faster than they really are. It would create the illusion of accelerated expansion, and poof! Dark energy isn't some mysterious force anymore. It's a cosmic mirage, a trick of our own local, slow time perspective. The Hubble tension isn't a problem. It's a clue. All right, so if dark energy could be an illusion, what about its partner in crime, dark matter? Could that also be one giant misunderstanding? Could we have been looking at gravity itself the wrong way this whole time?
For a long time, this amazing picture, the bullet cluster, has been Exhibit A for dark matter. The pink stuff you see is normal matter, hot gas that slams together in this cosmic car crash. But the blue stuff, that's where all the gravity is. And you can see they're separated. This has been called the smoking gun for invisible dark matter. Case closed, right?
Well, what if it's the smoking gun for something completely different? A really bold alternative theory, called emergent gravity, looks at this exact same picture and sees something else entirely.
This idea is a real mind-bender. It says gravity isn't one of the basic forces of nature. Instead, it emerges from something deeper, from the flow of energy and information. The best way to think about it is like temperature. A single water molecule isn't hot or cold, but get trillions of them moving together, and the property we call temperature emerges. In this view, gravity is like that. It's a large-scale effect, not a fundamental force.
So let's go back to our smoking gun picture, but with this new idea in mind. In emergent gravity, that strong gravity effect isn't caused by a blob of invisible matter. Nope. It's caused by the underlying energy field of the galaxies themselves. That energy field can pass right through the collision, while the hot gas slams into itself. So you get the exact same separation of gravity and matter, but you don't need dark matter to explain it. Not at all.
So where does all this leave us? On one hand, we've got an incredibly successful standard model that has worked beautifully for decades, but it's starting to show these deep cracks. And on the other hand, we've got these wild, tantalizing new ideas that question the very nature of time and gravity.
And this, right here, is the absolute beauty of science playing out on a cosmic scale. It isn't about finding one theory and sticking with it no matter what. It's this constant, amazing cycle of building something, testing it, finding the cracks, and then proposing bold, even crazy new ideas to try and build something even better.
So the big takeaway here isn't that our understanding of the universe is broken. It's that we are living in one of the most exciting times for cosmology ever. The Standard Model is still the best map of the cosmos we've ever had, but it's becoming pretty clear that the map isn't finished. We're the explorers now, venturing out into the parts of the map that say, "Here be dragons."
This isn't a crisis. This is an opportunity. This is science at its most thrilling, when our biggest ideas are on the table. And it leaves us with one final, huge question. Are we just patching up a few holes in our old map, or are we about to draw a completely new one? The final answer is not yet written.